Hello, Kemar, neurologist at Hopkins, an AI researcher, and recently I left uh, my clinical duties to pursue a startup called NeuroAgent AI to essentially revolutionize the use of AI in neurology care. Here are my disclosures. So I'm going to start off by showing you these two figures, which kind of identifies how eye movements, how the circuits for eye movements are represented in the brain. And this is just for two different eye movement types. This doesn't include all the eye movements that one could produce, but just for these two, you could see how much brain is involved in processing those two eye movement types. So keep that in mind as we delve into the reasons why I chose to study this specific area by using eye movements as a biomarker for brain disease. This has been published a lot. If you guys are interested in looking at eye movements in neurologic diseases, you could read John Lee and David Z's book, which kind of goes over most brain diseases and some diseases outside the brain that affects the nervous system that has specific eye movement signatures that could be leveraged with or without AI. But in this case, we're using AI to make diagnosis more precise and perhaps even more personalized. Uh, the main focus of the talk, though, will be to kind of go over all the limitations that we've encountered in trying to do that over the years. And so the first one we're going to discuss is a limited eye movement data set. There's privacy, and then there's also unreliable waveform data. So piggybacking from the unreliable waveform data, we get eye movement data using eye tracking, and the data itself is either a video recording of the raw movement and or extracted movement pose features from eye tracking. And those features could be extracted in different ways. So from 1901, people have been doing this using images from a photochronograph. And then with EOG, they looked at potential difference of the eyeball as it moves. They still use this in EEG. And then the gold standard has been developed at Hopkins, the magnetic surgical, but you can see here that it's a contact lens made of copper that's placed over the eye. It's not comfortable for patients, especially for scalable portable testing. And so it's not something that we could deploy easily in the clinical workspace to collect data. So that evolved into video oculography, which is what most people use currently for both our research and clinical eye tracking. And that uses just tracks position of the pupil or other eye features to infer eye movement. And so this is some image from our video oculography system that we have in clinic. And here on the left, this is a clinical grade device. You can see that the image quality isn't always so great, and this is done under clinical environment, clinical scenarios. And so if we were supposed to extract the waveforms from these videos over here, for example, I wouldn't be able to get the most or the cleanest data to be used for machine learning. And so we have to figure out a way around that. And so that's what we kind of did. And we also showed here that if you downsample a waveform, so this is a waveform of eye movement type called nystagmus, which has this characteristic sawtooth pattern. You see here, if we move from 240 to 15 hertz, that we lose the sawtooth pattern. As a clinician, we wouldn't be able to tell what's really going on by looking at this, if this patient had nystagmus or not. And so that in itself would be a barrier to using this in low resource areas for diagnosis. So what we came up with back then was a way around that by using the videos themselves without relying on the waveforms. And so we came up with a deep learning model that used a convolutional neural network to essentially look at each individual frame in the video and combine each individual frame to infer movement across those frames. And for the video data set that we use, it was 60 hertz. So we're looking at essentially movement across 16.67 milliseconds. And we use that to build a model to distinguish between movement, the abnormal movement that we were looking for, in this case, nystagmus, versus no nystagmus, which is normal. And back then, we got a very good AUC. We've also experimented with what would happen if we downsampled the videos, similarly to how we downsampled the waveform. And we build a model with those, and we see that our model didn't perform so great. It was the accuracy 67.9%, but believe it or not, this is much better than trainees or emergency room physicians back then. Since our initial 2020 model, others have improved upon it, and we developed a newer version of it using a 3D CNN in 2024. We also understood our models a little bit more. So here, for example, we trained the model to look at one beat of nystagmus, which is a slow phase and a quick phase. And with our grad chem intensity here is basically what the model is looking at. You can see that it starts to look or pay attention when the slow phase starts and stop paying attention at the end of the slow phase. So it's looking at a beat. It's looking at this the nystagmus, the video, the same way a clinician would. And so that's very, very important when you're building these computer vision based medical applications, because we have to ensure that the model is doing the same things a clinician would. And then regarding the data set issue, people in the past have tried to augment data sets with synthetic data. And you see here on the right of the screen rather, the distinction between synthetic and real. You can't really tell with regards to different data sets type. But when you combine the two data types and build a model, the model tends to perform better. And so this kind of tells us if we don't have a lot of data, we could augment it with synthetic data. And we've done something similar since then, but instead of using synthetic plus real, we modeled purely synthetic data. So here we wanted to distinguish a very simple task, whether the eyeball is twisted up or twisted down. So intorsion or extorsion, which infers essentially rotation of the eyeball either towards the nose or away from the nose. This is important because it could help us distinguish between a problem happening inside the brain or a problem happening outside the brain when someone has double vision, for example. And from this, we had a very good AUC, 0.98%, and it also generalizes very well on real patient data. So we were able to tell from that experiment that we can diagnose disease or detect clinical abnormalities from models built from synthetic data without any patient data. And so regarding biometrics and eye features, so for any model, not just in the medical space, but also in the non-medical space, for us to be able to validate these models and ensure that they're performing at benchmark levels, we need other researchers to be able to use them and test them in the wild. And it's very difficult to do that in the medical space because all the data has biometric features, and so we have to figure out a way around that, the privacy layer. And so, we don't want to release patient data and then their data becomes leaked into vulnerable spaces, if you will. Also of note, your eye movement pattern, the way you observe a scene, is also unique to you. So the red and the blue here in this video is representing two individuals watching this trailer. And you can see that the pattern in which they fixate and move their eyes between fixation points, saccades and fixation, is way different. And so that specific pattern is unique to an individual. And we also want to preserve that when we're building eye movement models. So our solution was to develop this pose-guided video generation method where we generated the waveform and used those generated waveform to generate videos. And so here on the extreme top left rather, we have the waveform of the eye movement type that we wanted to generate. This is saccade. We're modeling asymmetry or inaccuracy of saccades rather. And so we took that, generate the waveform based on physics and our understanding of what saccades are and what they should look like. And then we use that essentially to guide a pupil mask, essentially a segmentation of a pupil to move in the same way at that frequency. And then we use that to generate video using open source video dataset using generative AI, specifically diffusion models. And this is what we came up with. You can see here that they look somewhat realistic. It's very hard to tell the difference between the two if you're not an expert, but the movements themselves are accurate. Some, perhaps the features of the eye may look somewhat synthetic in the synthetic one, but that doesn't take away from its performance. And so the first task that we wanted to like test this on was on a disease condition called myasthenia gravis. That's been a passion of mine, which is a rare disease that affects the nerve muscle junction and could also affect the eyeball. And the whole premise of this disease is the more you use a muscle, the weaker it becomes. And so the current physiologic testing that are used for diagnosis relies upon the muscle's uh, fatigability over time with use. And so with this stimulus here, if you look at that stimulus, any individual, normal or abnormal, they produce this eye movement here, which is nystagmus, which is physiologic. And so if they're looking at this image for 2 minutes sustained, this involuntary movement that occurs will fatigue over time. And so we could measure the fatigue by extracting the waveform and see how that kind of pans off over time and use that as a biomarker for this disease. And so we did this with our initial 2D model back in 2021. The accuracy wasn't so hot, 67%. When we used the newer 3D model that we created in 2024, it went up to 85%, but that's still not perfect. So we need to make it a little bit better, right? And so we did the experiment that our Nature colleagues did, where they added synthetic plus real, and we did that. It went from 85% to 90%. But then we wanted to just make it purely synthetic, right? We wanted to see if we only use synthetic data, can we get similar results or better? And so here we have a normal patient producing the eye movement and a normal patient producing the eye movement. You could see also that in some abnormal patients that have this droopy or ptosis of the eyelid that we didn't want to capture. We wanted this to be a pure eye movement experiment. So we extracted what eye movements should look like in one patient with MG and one without, a normal and a disease. And essentially, these two waveforms we were used to create the boundaries for normal and abnormal. And we use that to generate the data set to essentially build a synthetic model. And so our model, when we built it, we wanted to see what it paid attention to. And the red is where the model was looking the most. And if you could see here, it was mainly looking at the pupil, which is where we wanted it to look because that's where the eye movements are. Once it looked at the eyelid right here, right? But nothing is perfect. We wanted to look at the pupil for the most part, and it did. And so with that, here's our results. The performance with lots of experiments. We got specificities and sensitivities that were close to or better than the gold standard. And so here's the gold standard over here, single fiber EMG, sensitivity, specificity. And here's our two best performing models, which sort of outperformed them in a sense. We need more data to validate that, obviously. And then even more interestingly, when we checked a small population, around 20 patients who were treated with disease modifiers for this condition, it was still able to pick up the disease in a very small percentage, which that alone was also much better than the blood test and other testing that we use to diagnose this. So very, very promising, right? The other thing we worked on was, in order for us to do this, we have to figure out a way to collect the data at home without needing to like fancy devices. So we developed our own set of goggles, set of eye tracking technology to be able to autonomously collect the data from patients without the need for a technician. And so this will enable us to reach patients, especially for rare diseases that are not able to come into our clinics. And so they could use their device at home or a device that we send them to give us the data. And then in the future, we want to like do this for a multitude of diseases, not just for diagnosis, but also for essentially triage in patients to determine who needs to be seen now, who could wait based on the acuity of their condition. And then eventually, we also want to use this to advance various neural AI interfaces for eye movement issues, but then this could also extrapolate into other neurologic disorders as well. In summary, eye movements can serve as a physiologic biomarker. Synthetic neurologic disease-specific eye movement data can be used to train robust AI algorithms. We've seen that multiple times. And eye movement data can be collected autonomously and remotely. That's all I have. Thank you.
Ago, we made a commitment that we were going to make this Maryland's decade, but that the only way that this could be Maryland's decade was if it was Baltimore's time. We made this truly work together to make this one of the